All right, so at this point, you should feel fairly comfortable with multiplying polynomials without having too much trouble. What we're going to look at today is what do you, or basically a shortcut way that you can multiply out when you have like a binomial raised to the power. So, like if you had like 2x plus 3 and it was raised to like the seventh power, right? Right now, in order to be able to do that problem, it would be kind of a lot of work for us, right? So, if I wanted to do something like 2x plus 3 to, oh, let's go with the fifth power, right? In order to do that, right now, what we'd have to do is we'd have to say, okay, well, that means that I have 5 copies of this, right? And then I'd have to do a double distributive property here to simplify this bit. And then once I got this answer, I would multiply it by this one. And then once I got that answer, I'd multiply it by that one. And once I got that answer, I'd multiply it by that one, which is, as you can guess, an awful lot of work, right? We've got 1, 2, 3, 4, basically 4 different times that we'd have to do some multiplication just to figure out the answer to this one problem. So, what we're going to look at today is a shortcut that you can do specifically when you have problems like this. So, it has to be a binomial raised to some power, and you can use this shortcut. Okay, so the first thing that you need to know in order to use this shortcut is Pascal's triangle. Okay, so this is a really cool pattern. So it is got a lot of different patterns in it. So you can see some of them are pretty obvious, like there's ones along the outside edges, right? So I know I could fill in like ones here. All right, you could also notice that like this row right here, these numbers are going up by one, right? 1, 2, 3, 4. So then I can predict 5, 6, 7. Same thing going this way, right? 1, 2, 3, 4, 5, 6, 7. All right, you might notice that this is symmetrical, right? It's 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So it's symmetrical going in both directions. All right. The overarching pattern, though, that we use to actually build Pascal's triangle is that the sum of any two adjacent cells is their sum goes in the cell that's below and between them. Okay, so 1 plus 2 is 3, 3 plus 1 is 4, 1 plus 1 is 2. So if I want to fill in this cell, I can do 1 plus 4 is 5. Okay, and then 4 plus 6 is 10. And then 6 plus 4 is 10. 4 plus 1, 5. Okay, so you can kind of see how we're going to fill this in. So this would be 6. This would add to 15. This adds to 20. This adds to 15. That adds to 6. Okay, and then down here, 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is also 35. Right, there's 21. There's 7. Okay, so you can see again, it's symmetrical going both ways. Okay, so it's the same in either direction. All right, and again, you can see those patterns. So there's the 5, 6, 7 that we predicted was going to show up. A couple of other interesting patterns that show up on here. One of them is if you take a look at this next diagonal, so 1, 4, 10, 20, 30. Oh, no, I'm sorry, this one 1, 4, 6, 10, 15, 21, right? So those numbers, so 1, 3, 6, 10, 15, 21, right? To go from 1 to 3, you add 2. From 3 to 6, you add 3. From 6 to 10, you add 4, right? 10 to 15, you add 5. So you can kind of see there's a nice little pattern that's going on there. Okay, so that's kind of a cool one. These numbers are also called the triangular numbers. So this is just kind of a little bit of extra free, interesting stuff. But you know about square numbers, right? Square numbers are numbers that make squares. So like 4 is a square number because I can take 4 dots and make a square, right? 9 is a square number because I can take 9 dots and arrange them in a square. That's why they're called perfect squares, if you didn't know that. Okay, so these numbers, this 1, 3, 6, 10, 15, 21, these are called the triangular numbers because similarly, I can use them to make triangles. Okay, 1, just like with 1 squared, right? That's kind of the trivial case. I guess you could call it a triangle. But 3, I can take 3 dots and make them into a triangle. 6, I can take 6 dots and make them into a triangle. 10, right? I can take 10 dots and make those into a triangle. So those are called your triangular numbers. So this row right here, diagonal, right? You're adding 2, adding 3, adding 4, and those are your triangular numbers. There's actually a lot of other really cool patterns that you can look at in here. So sometime, when you have free time and you're just like, hey, I could go for some math right now, take a look around and see what you can figure out for some patterns. All right, great. So we've got Pascal's triangle. So the first thing you're going to need to be able to do is build Pascal's triangle. Okay, so make sure you know how to do that. But what we are going to use this for is we are going to use this, like I said, to expand our binomials, okay? So we're going to start by looking at just a generic one. So if we had something like ax plus b, okay, and then we were raising that to the fifth power, okay? I'm going to do a lot of color coding here. This can be a little bit confusing at first, all right? So you got to really keep a close eye on what's happening. So we're gonna use a little table just to help us with the organization here, okay? So the first thing that we're gonna do is this number up here, the 5, okay? This tells you what row from Pascal's triangle that you need, okay? So this number right here, the 5, tells you that you're gonna go for row 5 of Pascal's triangle. Now you can see that I numbered these rows. Please note that it starts with row 0, okay? So it starts with row 0, so then this is row 1, this is row 2. Okay, and the nice thing about that is that row 2 is the one with the 2 in it, row 3 has the 3 in it, row 4 has a 4 in it, row 5 has a 5 in it. Okay, so just make sure that you're okay with that. So if we want the row 5 of Pascal's triangle, that's going to be this one. So I'm going to start by just rewriting these numbers in a column like so. Okay, so that's the first thing that you're going to start with. So now what we're going to do is this middle column is we're going to take whatever our first term is, which is ax for this one, and we are going to raise it to descending exponents, starting with whatever our problem gives us. So this gives us to the 5th. So what we're going to do for the first one is we're going to raise ax to the 5th power. Okay, for the next one, we're going to raise ax to the 4th power. And then the next one, it'll be ax to the 3rd power, and then ax squared, and then ax to the 1st power, which is just ax. And then the last one would be ax to the 0 power, but anything to the 0 power is 1, right? Okay, so we start with a matching exponent, and then you drop each time. All right, and then the last column that we're going to do the same thing with the b, but going the other way. Okay, so for the b's, we're starting with b to the 0 power, which is 1. And then we're going to do b to the 1st power, b to the 2nd power, b to the 3rd power, b to the 4th power, b to the 5th power. Okay, so that setup, that is your pattern. So these numbers you get from a row of Pascal's triangle going off of whatever your exponent is. These ones, you take your first term and raise it to a matching exponent, and they drop each time. These ones, you take the second term and you raise it to the 0 power and you increase the exponent once each time. Okay, so it should work out that if this is to the 5th, then this is to the 5th. Okay, so then to get our actual answer, so the actual answer to this problem, if I wanted to actually figure out what ax plus b to the 5th power is, okay, what you do is you multiply each row and then add those terms together. Okay, so it's going to be the product of this first row, so 1 times ax to the 5th times 1, right? So that would be ax to the 5th. Whatever that would simplify out to, you'd have to actually use your exponent rules to simplify this. The next one would be 5 times ax to the 4th times b. So I'm doing plus 5 times ax to the 4th times b. And then the next one would be the next row. So 10 times ax to the 3rd times b squared. The next one would be 10 times ax squared b to the 3rd. And then 5 times ax times b to the 4th. And then plus 1 times b to the 5th. Okay, and that huge polynomial is what you would get if you actually multiplied this out. Okay, so it feels like this is kind of a lot of work. Like you might be looking at that and going like, wow, Miss King, that's a lot of work. But remember, this is what we're shortcutting, right? We're shortcutting having to multiply all this nonsense out like a whole bunch of times with a ton of different distributive properties, okay? So even though this is long, it's shortcutting a lot of steps for you, and setting it up really isn't that difficult. Okay, so that was a generic one. So now let's look at a specific example. Okay, so we're gonna do a specific example now. So I'm going to go with, hang on, I need new colors. This is important. All right, so let's start with 2x, and then we're going to do plus 3. So 2x plus 3, and I'm going to raise that to the 4th power. Okay, so 2x plus 3 raised to the 4th power. So setting up my little table. All right, so the first thing that I need is I need the row from my Pascal's triangle, right? My exponent here is 4. So I need row 4 from Pascal's triangle. And remember, that's the one with the 4 in it. So 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. Copy that down. Okay, so then I'm going to simplify this. So now this column is the first term, so 2x raised to a matching power. So 2x raised to the 4th power, and then 2x raised to the 3rd, and then 2x squared, and then 2x to the 1st, which is just 2x, and then 1. Okay, and then for my last term, it's going to be going the other way. So 3 to the 1st power is 1, 3 to the 2nd power is 3, 3 to the 3rd power, 3 to the 0 power, 3 to the 1st power, 3 to the 2nd power, 3 to the 3rd power, 3 to the 4th power. Okay, so then to write my answer, we just have to simplify this. So you're going to have to actually multiply this stuff out. So when I multiply across here, you have to actually multiply this out. 2x to the 4th power, that means 2x times 2x times 2x times 2x, right? So that's going to simplify to 16x to the 4th. Okay, and then I have to multiply 4 times 2 to the 3rd times 3, right? So 2 to the 3rd power is 8. So I am multiplying 8 times 4 times 3, which is 56. That's not right. It's 96, excuse me. My calculator is broken, and yeah, the number didn't show up right. Okay, so 96x to the 3rd. All right, and then I'm going to multiply 6 times 4 times 9. And again, you can throw that in a calculator. That works out to 216x squared. Okay, and then I'm going to multiply 4 times 2 times 3 to the 3rd is 27. So 4 times 2 times 27, which is also 216. And then 1 times 1 times 3 to the 4th, 3 to the 4th is 81. So there we go. That is my polynomial for this one. Okay, so if you actually were to multiply this out, do all your double distributive properties, that's what you'd end up getting. All right, so let's do one more of these. Okay, and this time I just want to tackle one that's going to have a negative in it. So we're going to do 3x and then minus 1. All right, and we will raise that to the 3rd power. Okay, so 3x minus 1 raised to the 3rd power. So it's just a touch different because of the minus. All right, so same way that we're going to start it. So the first thing that we need to do is fill in the row of Pascal's triangle. Okay, so I want 3. So I'm looking back up here to the row with the 3 in it. It should be 1, 3, 3, 1. Great. Okay, so 1, 3, 3, 1. All right, and then my middle column, I'm going to take 3x, and I'm raising it to the matching exponent, and then I'm dropping it each time. 3x to the 1st, and then 3x to the 0 is 1. All right, and then this last one, I'm doing -1, and we're starting at the 0 power. So -1 to the 0 power is still just 1. -1 to the 1st power, -1 to the 2nd power, and then, -1 to the 3rd power. Sorry, that should be a 1. Wrote the wrong number. All right, so then when we go to simplify this, okay, you just have to be careful about your exponents here, whether this is going to end up being positive or negative. So this top one, I'm going to have to multiply 3 to the 3rd power, that's 27. So that's going to be 27x to the 3rd. This one would be, this is 9, so 3 times 9 times -1 is -27x squared. Here I'm doing 3 times 3 times -1 squared is +1, so that's just +9x. And then 1 times 1 times -1 to the 3rd power is going to be negative, right? So that's just going to be a -1. Okay, and that's what that polynomial would work out to if you multiplied the whole thing out. Okay, so notice that in this one, your signs end up alternating. Okay, and that makes sense because if you think about what's going on here, right? Every other one is going to be even, and then it'll work out to a positive number. All right, so that is how you use Pascal's triangle to shortcut multiplying out binomials. Okay, so it only works with binomials, so it has to be set up in this format. All right, and it feels like a long process, but it actually is much, much faster and a nice little shortcut to know.